Hello, welcome to this video. Today we're going to look at a nice problem of expected score, like playing a game. So, the original place where I got this problem is a YouTube video by Numberphile called Darts in Higher Dimensions. I'll link that video in the description. Which is just a problem involving shooting darts and probability, shooting darts in a certain way, with the bullseye shrinking, and what is the expected score. So I'll link that if you want to properly watch it. It is interesting. And at the end of that video, another problem was proposed, in the same way. So this is how it goes. So we pick numbers between 0 and 1, including 0 and 1. So let's say for all I in the naturals, xi is in 0, 1. So all of the xi that we pick, so x1, x2, x3, and so on, are in 0, 1. Between 0 and 1, including 0 and 1. And then we keep adding those up. So we have x1, then we have x1, and then we pick another x2, and we add that, x1 plus x2. Then we pick another x3, and we add them, x1 plus x2 plus x3, and so on, until we pass the number 1. So the score is equal to n as long as x1 plus x2 on until xn is bigger than 1. But if this is the moment we pass, if we needed to add xn in order to pass 1, that means that x1 plus x2 plus until xn minus 1 is smaller than or equal to 1. So if these two are satisfied, our score is n. And same the other way. If our score is n, that means that this is what happens when we picked our numbers x1 up until xn. So with those rules in mind, now we want to know what is the expected score. So write like expected score. The expected score is, you can think of it as what we, if you do a bunch of games, like 1,000 games, and then you average all the scores out, what would the answer be? Or maybe the amount of scores you're averaging approaches infinity. What would that number be? You take the mean of that. What will it be? So that's sort of the expected score. That is the expected score, and we want to find it. Now, that's the problem that was proposed in that video, and that's the problem that I'm gonna solve. Now, I know I'm a little late, but maybe there were some people that were thinking about it, couldn't figure it out, and now can watch this video to see the solution, at least my solution. So let's begin. So first of all, we're gonna look that you can see that the expected score. A way to interpret it is each number times the probability that our score is that number. So basically it's 1 times the probability of n equaling 1, or score equaling 1, we'll just call it n equal 1, plus 2 times the probability that n is equal to 2, that the score is 2, and so on. so that's a way to interpret the expected score that is equal, and that's what we're going to use to find the expected score. So first of all, we're going to use a small trick, sort of a trick that was used in the original video, which goes like this. So let's see, what is the probability that n is equal to k? It seems a bit hard to see what is the probability of n exactly being equal to k. Well, we know that if n is equal to k, that means that n must be bigger than k minus 1, and n being, and not being, and it's not the case where n is bigger than k. So this basically means n is bigger than k minus 1. At the same time, n is not bigger than k, so this means n is smaller than or equal to k. If n is bigger than k minus 1, and n is smaller than or equal to k, and k is obviously a natural number, and so is n, we know that n has to be equal to k. And these two basically mean the same thing. If this, then this, and if this, then this. So the probability of this happening is the probability of this plus the probability of this. But then the probability of this, is like subtracting the probability where n is bigger than k. So we can say that this is the probability where n is bigger than k minus 1 minus the probability of n being bigger than k. So this means, yes, n is bigger than k minus 1, but no, n is not bigger than k. So that's what we have now, and that's what we're going to work with. And now we can substitute this in. So we can say that this is 1 times p of n is bigger than 0, minus 1 times the probability of n being bigger than 1, plus 2 times the probability of n being bigger than 1, minus 2 times the probability of n being bigger than 2, plus 3 times the probability of n being bigger than 2, minus 3 times the probability of n being bigger than 3, and so on. And so let's see what's happening here. So let's see, how many p of n bigger than 0 do we have? We have 1 of it. Just this beginning one. How many p of n bigger than 1 do we have? We have 2 minus 1. So we have plus p of n being bigger than 1. Then how many p of n bigger than 2 do we have? 3 minus 2. So plus p of n bigger than 2. And it's easy to see that this pattern will continue forever. So plus p of n bigger than 3, plus p of n bigger than 4, and so on. Now, let's see why p of n bigger than something is easier to calculate. If n is bigger than something, it means that we had to add on at least 1. It means that we had to add on at least 1 number from this line between 0 and 1 for it to be bigger than 1. Meaning that it had to be the case, and also had to be the case where when we added on the first n terms, it wasn't bigger than 1, meaning that it was smaller than or equal to 1. So we can say that the probability of n being bigger than k is equal to the probability where we had to add on at least one more number from this line to the sum x1 plus x2 all the way on to xn for it to be bigger than 1, and it wasn't bigger than 1 before. And this is satisfied, and this is already satisfied where the sum of x1 plus x2 plus x3 all the way on to xn is already not bigger than 1. And this is the probability of x1 plus x2 on until xn being smaller than or equal to 1. And we have to calculate this for each number for each number of 0, 1, 2, and so on. So now we're going to calculate each one of those by their own, on their own, and then add them all up. So let's start with the first few cases. So n is bigger than 0. Well, if n is bigger than 0, that already has to be the case. Because if we're not adding on anything, of course we're going to have to add on. So if we're not adding any new numbers, of course we're going to. If we're adding 0 numbers, of course we're going to have to add more numbers for it to pass 1. So this is 1, meaning that it has to be the case. Another way to look at this is n has to be a natural number. We're always adding on at least one number, so n already has to be bigger than 0. Probability of n being bigger than 1 is the probability of picking a number, x1, from 0 to 1, and then is that number smaller than or equal to 1? Well, the answer is yes, always. That's just by the definition of x1 being between 0 and 1, it has to be smaller than or equal to 1. So this is also 1. But now we're getting on to a harder part. So let's erase this. How can we calculate p of n being bigger than 2? Meaning that we're choosing x1 and x2. What is the probability that it's smaller than or equal to 1? Well, we're going to interpret geometry into this. We're going to use geometry. In the original, and eventually you're going to see when n is bigger than 3, n is bigger than 4, and so on. What we're going to have is looking at higher and higher dimensions, which is also what the original video did when solving the problem. So x1 plus x2, first of all, x1 and x2 are between 0 and 1, meaning that if we look at the point x1, x2 in the xy plane, they are inside the square where this is 1, 1, this is 0, 0, this is 1, 0, and this is 0, 1. So they are in this square somewhere. This point is in the square somewhere. Now how can we interpret in this square if x1 plus x2 is smaller than or equal to 1? Well, first of all, let's draw the line where x1 plus x2 is equal to 1. If x1 plus x2 is equal to 1, it's this line. It's this line right here. It's this diagonal. Now, x1 plus x2 being smaller than 1, we can interpret this as the point being below the line. So if this is our point, it means that its y-coordinate, its x2, is smaller than what it needs to be for it to add on to, is smaller than the x2 it needs to be for it to add to x1 and get 1, meaning that it's small, that its sum with x1 is smaller than 1. We can say this as, if this point is here, it's below the line, meaning that the y-coordinate, which is x2, is smaller than the y-coordinate, of the point which is on this line, and its x value is x1, meaning that its y would be 1 minus x1, and we just add x1 to both sides, and x1 plus x2 is smaller than 1. And similarly, if a point is above the line, that means that our x2 would be bigger than 1 minus x1, and we add on x1 to both sides, and x1 plus x2 is bigger than 1. Meaning that at any point we choose, x1 comma x2, their sum, the sum of x1 and x2 is smaller than or equal to 1 if and only if they're on this line or below it. And geometrically, we can interpret this as what is the probability of them being in this triangle when we know they're inside the square and we pick a point randomly, because we're picking x1 and x2 randomly. Well, that is just dividing this area by this area. By the area of a right triangle, because this is 90 degrees, it's the length of this, which is 1, times the length of this, which is 1, divided by 2. So this is 1 times 1 over 2, divided by the area of the square, which by the area of a square is the length of its side times the length of its side. So it's 1 times 1. And then this is 1, and we get that this is 1/2. So now let's erase it. Let's quickly erase this and try to understand what's going on with n being bigger than 3. Okay, now let's try to understand x1 plus x2 plus x3 being smaller than or equal to 1. What's that probability? AKA probability of n being bigger than 3. So, like we thought of p of n bigger than 2 as an xy plane where we pick a point in a square, and then we identify we're identifying what geometric shape the point needs to be for the sum of the coordinates to be smaller than or equal to 1. We're going to do the same thing for n is equal to 3. Instead of 2 dimensions, we're looking at 3 dimensions. So we have y, so we have x, y, z, and what we're looking at is picking x1, x2, x3 is like picking a random point x1, x2, x3 in this 3-dimensional space. And because each one of those is between 0 and 1, it's the same thing as this point is inside a cube. It's inside this cube, which has this being 0, 0, 0, 1, 1, 1, and every combination of 0 and 1 in all of those. And our point is somewhere in there. And we want to find what geometric shape contains all the points that make x1 plus x2 plus x3 be smaller than or equal to 1. What shape contains all of those, and what shape only contains those. So the shape that contains all of those and only those. And then our probability of n being bigger than 3 is the probability of them being in that geometric shape, which is just dividing the volumes. of that shape by the volume of the cube, like we did with 2 dimensions. So what we're going to do, first of all, again, like in 2 dimensions, is find 3 points that satisfy this, and then the plane that goes through those 3 points will be the plane that satisfies x1 plus x2 plus x3 is 1. So we can very easily pick those points. We can pick 1, 0, 0, 0, 1, 0, and 0, 0, 1. And so this creates this sort of triangle. And then the plane running through those 3 points is the plane where the sum of the 3 coordinates is 1. And then similarly, when going down, the y coordinate, the x2, goes down, meaning that the sum of the 3 coordinates it will be smaller than 1. And when the point goes up, x1 plus x2 plus x3 will go up because x2 will go up and it will be bigger than 1. Meaning that this shape that has the where these 3 lengths are 1 and this is the origin, this shape contains all of the points that satisfy x1 plus x2 plus x3 being smaller than or equal to 1, and only them. Because any other point that is not in this shape has to be, not on this shape including the plane, will have to be above this plane, meaning that it would have to be the case where the sum of the 3 coordinates is bigger than 1. Which means any point that's not in this shape. So any point that's not in this shape, the 3 coordinates are 1, are bigger than 1, and any point that's in this shape, the sum of the 3 coordinates is smaller than or equal to 1. So it contains all those points and only those points. Meaning that now we can divide the volume of this shape by the volume of the cube. The volume of the cube is just the sum, it's just the product of all of its length 3 times. So it's the length of this cube cubed, but it's 1 to the power of 3, which is 1. So what we're actually looking for is the volume of this shape, this pyramid. And we can find it using integration. So let's just for a second focus on the case where those 3 lengths both equal to x and not 1. Because that will help us when looking at n is bigger than 4 to help understand it. So what we can do is split it up into very thin pyramids that look like this, with this being the width. So they're very small, and we'll call that width dx, and then that width times the area of each one of those, times the area of the triangle. So we have something like this, and so because dx will approach 0, dx, which will be this width, times the area of this triangle will be the volume of this shape. And then when we cut it finer and finer, so dx gets smaller and smaller, we'll have more and more of these shapes, and this cutting will be more accurate. So the cutting goes like this. And so we'll get running lines through these and running lines through these, and on this diagonal. So we'll split it up into these shapes. And as we split it finer and finer, so this dx gets smaller and smaller, this approximation will get better and better. And when dx is right when it's approaching 0, that will be the exact volume. Meaning that, and because x goes from, let's call our parameter t, so I'll actually call this dt. Because our dt goes from 0 to 1, to x, so it's from 0, which is a small height, to x. That means we're integrating from 0 to x of now we need to find what actually this is. The area of this triangle times dt. In the area of a right triangle, because this is a right angle, is this times this over 2. Both of those are t, so it's t squared over 2 dt. So just to reiterate, we're splitting this up into finer and finer shapes like this, and we're calling this with dt, and this dt gets smaller and smaller, and as the dt gets smaller and smaller, the sum of those volumes gets better and better, and then right when dt approaches 0, is right at the limit of 0, that sum of those volumes will be the exact volume, and that is equal to just integrating, because t goes from 0 to x, this is integrating from 0 to x of t squared over 2 dt, and this t squared over 2 dt comes from just the volume of this shape, where we have to calculate the area of a triangle like this, where this is t and this is t and this is a right angle, meaning that this is t squared over 2, and then we're multiplying by the width dt. And so that's that's the volume. So by simple integration rules, we get this is t cubed over 6, just by adding 1 to this exponent, which will turn it into a 3, and then dividing by this 3, and we get t cubed over 6 from 0 to x. When t is equal to 0, this is 0. When t is equal to x, this is x cubed over 6. And so our final answer is x cubed over 6 minus 0. But subtracting 0 doesn't affect the answer. So this is x cubed minus 6. And in our case, where we want the volume where x is equal to 1, this will be 1/6. So the probability of n being bigger than 3 is 1 over 6. Now that we have all of that, let's try to understand what is going on in P of n bigger than 4. In P of n bigger than 4, we're going to do the same thing, which is look in a 4-dimensional space at a point x1, x2, x3, x4. Now, of course, I can't draw this 4-dimensional space because we only live in a measly 3-dimensional space. Poor choice. But the same thing applies. So where this point is in a 4-dimensional cube, where all the coordinates of the points of that I'll call it hypercube are just the mixes of 1 and 0, so 0, 0, 0, 0, 1, 1, 1, 1, and everything in between. So those are the coordinates of the points of that cube. And then we're looking to find which geometric shape contains all the points and only the points where the sum of the coordinates is smaller than or equal to 1. And then what we do is take the three-dimensional space that passes through the 4 points 1 0 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1, because those satisfy when it's equal to 1, meaning that, and they form in a 4-dimensional space. Those 4 points form a 3-dimensional space, which satisfies that the sum of the coordinates is equal to 1. And then below that 3-dimensional space, each point in the below it is one of the coordinates will be smaller, meaning that the sum will overall be smaller than 1. And if it's above that space, then one of those coordinates will be bigger, meaning that the sum of the coordinates will also overall get bigger. Meaning that the 4-dimensional space, which is under that 3-dimensional space where the sum of the coordinates is 1, that's the 4-dimensional space we're looking for. And then we divide by the volumes of that 4-dimensional space, which will look similar, where we have one line, second line, third line. Then we'll have like a fourth line, which is perpendicular to all 3, like we had in 3 dimensions. And then we connect all those lines up like this. Of course, we can. Of course, this is sort of what it will look like. We can't really know what it will look like because we live in 3 dimensions. This sort of what it will look like, and then we need to find the 4-dimensional volume of this and divide it by the volume of the cube, which is 1. So we're looking for the volume of this, and then by a similar integration process, if all of those side lengths are x, and we do a similar process where we cut, and then we get those shapes that we had in 3 dimensions, like this. We get those with the width dt and all of that. Of course, we can draw that because again, our 3-dimensional world and our 3-dimensional mind can't comprehend 4 dimensions. But the integral will be the same, where it's the integral from 0 to x of the volume of that shape that we had in p of n bigger than 3, which is we want in the t, so it's t cubed over 6 dt. And it's a simple integral, which is x to the 4th over 24. And then because we want x being 1, because the sine length is 1, we will get to this is 1 over 24. And then for 5 dimensions, we will get we'll have the same thing with the cutting, the volume, and the plane, all in this 4-dimensional space where the sum of the 5 coordinates is 1, and that the final result will be 1 over 24 times 1/5, because as you may have noticed, we're multiplying by 1 over 1, 1 over 2, 1 over 3, and 1 over 4, and this is going to continue on. And by this pattern, we can say that we can prove by induction. I'm not going to do it, it's pretty simple to prove. This is 1 plus 1 over 1 factorial, plus 1 over 2 factorial, plus 1 over 3 factorial, plus 1 over 4 factorial, plus 1 over 5 factorial, and so on. And that's the probability of each one of them. By the cutting and slicing and looking at it geometrically in a higher dimensional space. So this is equal to 1 plus 1 over 1 factorial, plus 1 over 2 factorial, 1 over 3 factorial, and so on. Now, if you're familiar a bit with like the Maclaurin series and Taylor series, this should scream something at you now. Because, let's look at the expansion Taylor series for each dx, which is 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. This is e to the x. And if x is equal to 1, all of those powers are 1. And we get that this sum is e to the first power, which is a final result of e. Which is very unexpected considering we're just picking numbers between 0 and 1 in our scores, just when the sum passes, the sum of all the ones we picked passes 1, but the one before it didn't pass. But that's the final result. I hope everything was clear because it is a bit hard to understand what's going on with the multi-dimensional thing. But that's it. And if you want more content like this, please subscribe to my channel. I'll be uploading more interesting problems and things. Maybe not like this, because this is pretty hard to think about if you try to think about it multidimensionally. But we'll be doing interesting problems in the future. And finally, that's it.